was made a little over 50 years ago by astronaut David Scott from one of the Apollo missions, dropping a feather and a hammer on the moon to show that they actually fall at the same rate. Gravity accelerates them the same. It's just that air friction on the Earth makes the feather fall slower, so that was an important illustration. But there was a second, more subtle thing going on that maybe you noticed that pertains to today's lecture, and that is that there's exactly one point on the hammer and one point on the feather that falls straight down when they fell. That is the center of mass of the two objects, and that's going to be one of the applications we do today of multiple integrals. We'll start out just doing this for two-dimensional objects. We'll say a lamina is an object that's so thin it can be modeled as a plane region. And suppose delta of xy is a density function. It's some units of amount of something per unit area, like kilograms per square meter, or maybe it's people per square mile. The total amount is the double integral then of the density function over that plane region. So it might be, if this is people per square mile, you integrate and get the total people. If it's kilograms per square meter, you integrate it and get the total kilograms of the object, of the mass of the object. And then if delta is a constant, then we say that it has uniform density. So here's the motivation for that definition. The idea is you have a lamina represented by a plane region here, R. You partition it up into little rectangles of width delta xi, delta yj for the ijth one. And then you estimate the area as by taking the mass of the ijth object, you could call this delta mij. Here's the mass of the approximate mass of this ijth plane region. Delta is approximately constant in this little bitty region. So the density in kilograms per square meter times square meters gives you the kilograms of this little tiny piece. Pretty approximately, because over this little piece delta doesn't change much if it's, say, continuous. Now if you add all the little pieces, the approximate mass of each, then you get an approximate mass of the whole thing. And if you take the limit as the number of pieces goes to infinity, np, if you have capital N times capital N total subpieces, by dividing this m pieces this way and n pieces this way, then little n goes to infinity. With the width of the widest interval going to 0, what you find is that actually this limit of the sum is the same number for a continuous delta, no matter how you partition this up, no matter which points you pick intermediate. So we say, oh, that ought to be what we call the actual mass of the lamina then, because after all, it has the same reason when we use that same mass when we used to evaluate it either way, with any partition and any points in the little subregions picked. So let's bring this back now. With this definition, we can also extend it to cover three-dimensional regions. In 3 dimensions, we just take a triple integral of a density function in, say, kilograms per cubic meter. Here's an example now of the first one. This is similar to your homework. If I want to integrate over the unit square, 1 by 1, right? Just take the density function to be x squared plus y squared, the distance squared from the origin. If I want to integrate to get the mass, I double integrate x squared plus y squared, the density, over that little square. The square goes from 0 to 1 and 0 to 1. When you take that integral, the inside integral is a partial integral treating y as a constant, so integral of x squared is x cubed over 3, but integral y squared is x times y squared. Evaluate this in 0 to 1, you get 1/3 plus y squared, and then you have a calculus 1 integral here. The whole thing comes out to have mass 2/3 kilogram. Here's a little harder example. Suppose delta is a charge density, and suppose we're in 3 dimensions now. Maybe we're in this solid here, W, which is x squared plus y squared plus z squared less than or equal to 0.16. What's that? Well, if you had equals, this would be a sphere, right? X squared plus y squared plus z squared equals 0.4 squared. A sphere of radius r Less than or equal to gives you the ball, the closed ball bounded by the sphere of radius 0.4. The density could be this many coulombs per square meter, say 2 times 10 to the minus 10th over square root x squared plus y squared plus z squared. Then the total enclosed charge is the integral, triple integral of the charge density over the closed ball. How do you integrate over a closed ball? You let theta go all the way around from 0 to 2 pi, phi go all the way from the top to the bottom of the ball, 0 to pi, and rho goes from the inside, the center of the ball at 0, to the outside sphere, 0.4. This triple integral can be broken up into the product of 3 because, in this case, the integrand splits into a product of a function of phi alone, a function of rho alone, and 1. 2 to the minus 10th comes out. And the endpoints are constant. So you say, for instance, I can pull the sine phi out of the inner integral because it's a partial integral and phi is treated as a constant in there. So I pull that out of here, and then what's left, the integral over rho evaluated at constant endpoints is a constant, so I can pull the rho integral outside. And then d theta comes through because none of this depends on theta. You write it as this product of 3 integrals, sine phi from 0 to pi, just 1 from 0 to 2 pi of theta, and 0 to 0.4, you integrate rho d rho. I rho squared over rho is rho. These 3 integrals are easy calculus integrals. You get 6.4 pi times 10 to the minus 9 coulombs. Now we can do more than just calculate the mass. We can also calculate the moment of mass. Right? Suppose we want to calculate the moment of mass in the y direction. This is about the x-axis. So this is the moment of mass about y equals 0. You can integrate y minus y0 and get the moment of mass about y0, for instance. So the moment of mass in the y direction, mx, is the double integral of y times the density. You just put a y in there, and now you get the moment. Similarly, the moment of mass in the x direction about the y-axis, my, is double integral of x times the density function. And then the center of mass, that point we were talking about in the video, that goes straight down, is my over m for the x center of mass and mx over m for the y center of mass. And if you were to take an oblong object and throw it, that center of mass executes a nice trajectory because uniform gravity acts as though this was a point object with mass all at the center, all of its point of center of mass. So here's my uniform gravitational field. And so that center of mass travels a nice parabola. Every other point kind of wobbles around it as this thing flies. This has implications in statistics. Actually, my over m is the mean mass point in the x direction. Mx over m is the mean mass point in the y direction. And so this actually has applications there too. Here's a harder example. Now suppose I want to find the center of mass with constant density, delta of xy equal 2. Below a parabola, y equals 1 minus x squared, and the line y equals 0. And I go to calculate the mass, I double integrate the density. Oh, I'm just double integrating 2. I could pull the 2 out, and this would be integral of 1 dx dy, dx, and this would give me the density times the area of the plane region. That's what we want for a uniform density, is just take the density times the area, gives you the mass. Well, so I could pull the 2 out, I didn't choose to, but we could just do the double integral. Integral of 2y is y, integral of 2 is 2y, plug in the endpoints and take the difference, you get this. Integral, it's a calculus 1 integral, whose evaluation is 8/3. Now here's the nice thing, when you go to calculate the moment of mass, I want to calculate center of mass thing, so I could tilt this over and balance it on this point on my finger. The moment along the x-axis is at x equals 0, right? Just by symmetry. This piece balances this point piece when it's constant density, and so I put my finger right here. And if the center of mass is going to be at x equals 0. That means that my over m has to be 0. So that means the numerator is 0. The moment of mass about this balancing point is 0. Now if gravity points in this direction, I need to balance this along the y-axis, and that's harder to tell. I have to calculate it. The double integral of y times the density function comes out to be, well, it's just this integral again. This is the nice thing when you go to calculate mx here, it's just the same integral here, stick y in. This again is a iterated integral of 2y's, y squared, plug in the endpoints and take the difference, leads me to a calculus 1 integral that comes out to be 16/15. Now if I take my over m, I get 0 for the x coordinate of center of mass, take mx over m for the y coordinate is, well, this one over this one, 16/5 over 8/3 comes out to be 2/5. So the center of mass is at 0, 2/5. This example is an interesting illustration, this constant density, because it leads us to the next topic, which is a centroid. The centroid of a plane region is what you get by taking this formula that we just did, right? This is the moment of mass, my, divided by the mass, m. If delta is a constant, c I wrote here, then you can take the c's out of the integral and cancel them. So I scratched it out here. And what you get is this, double integral of x dA over double integral dA is just the area. So the x coordinate of the centroid, which is the balancing point when you have uniform density, is just double integral x dA over a, is in fact what you get by taking the center of mass formula and replacing delta with 1. So center of mass formula is this for the x coordinate, this for the y coordinate. If you put delta equals 1, you get the position of the centroid, which is the center of mass for any constant density object. Let's do a calculation with that to find the centroid. And by the way, in statistics, x bar and y bar are typically used to denote the mean point. This is actually the mean mass point in the x direction and y direction, and so this actually has statistical significance to use that notation. Similarly, in 3 dimensions, x bar, y bar, and z bar can be a triple integral of x times replace density with 1 dV over triple integral of 1 gives you the volume. Y bar is triple integral of y over v, and z bar is a triple integral of z over v. So we could, for instance, find the centroid of this ice cream cone found on the outside by phi equals pi over 6, and on the top by rho equals 3, the sphere. So this is a sphere on top, a cone on the outside. For this one, we notice immediately we balance it for, right, since we're finding the centroid. This is the balancing point of an object that has density 1, essentially. And we can balance it right there. So x bar and y bar must be 0. We just have to find z bar, the balancing point along the z-axis. So we need the volume for that. We triple integrate 1 to get the volume. Well, the dV, the infinitesimal volume element, is rho squared sine phi d rho d, is rho squared sine phi d rho d phi d theta. We integrate between the limits. Phi goes from 0 down to the edge of the cone, pi over 6. Theta goes all the way around, and then rho goes from the origin out to the sphere on top. And so we have these limits, 0 to 2 pi for theta, 0 to pi over 6 for phi, and 0 to 3, the radius of the sphere on top. This nicely breaks up into the product of 3 integrals since I have constant endpoints here. Right? I can pull the d theta through because there's no theta in here. Pull the d phi through with the sine phi since there's no phi otherwise. And we get the product of these 3 integrals. Integral of rho squared from 0 to 3 comes out to be 9. This one comes out, integral of sine phi is 1 minus square root of 3 over 2. And integral from 0 to 2 pi d theta is 2 pi. We get a volume of 9 pi times 2 minus square root 3. Now, if we want to calculate triple integral of z for the top of that, then we just write this same integral, put in z. Well, z is rho cosine phi. So we'll take triple integral of rho cosine phi this time over the same integration limits. time, we get this integral here, when we split it into three parts, integral sine phi, cosine phi. This one can be integrated at least two different ways. You can let u equal sine phi, then du is cosine phi d phi. You just have to integrate u du. Or you can say from trigonometry, 2 sine phi cosine phi would have been sine 2 phi. So I could say this is actually integrating 1/2 sine 2 phi, whose integral is -1/4 cosine 2 phi immediately. And I evaluate that at the endpoints and take the difference. Evaluate rho cubed from 0 to 3 and get 81/4. Integrate 0 to pi d theta, get 2 pi. Multiply all this all together, I get 81 pi over 16 is the moment in the z direction. Take the moment divided by the mass using density equals 1 to get the centroid. And this 2 minus square root 3 on the bottom needs to be rationalized. We can multiply, here, we'll simplify here a little, canceling 81 over 9 is 9, for instance. 16 goes down to the bottom. 2 minus square root 3 in the denominator can be gotten rid of by multiplying top and bottom by 2 plus square root 3. If I do that, 2 plus square root 3 times 2 minus square root 3, the square root 3 cancel out. I just get 1 in this case. And I wind up with 9 times 2 plus square root 3 all over 16 for the center of mass then, the centroid. There's this interesting application of the centroid, by the way. If you take a plane region and move it around in the plane, if you take the path that the centroid travels with this plane region always perpendicular to the path, and the path never turns so sharply that the cross sections of the volume generated, the solid generated by moving this along the path, intersect. So you don't turn so sharply that the cross sections intersect. The solid that you get by moving this plane region along a path is the distance traveled by the centroid times the plane area of the region. We don't have any problems on that in this section, but it's a very important geometrical application. The centroid times the path length times the plane region gives you the volume of a solid generated. Well, there's a little material at the end that's kind of interesting on probability theory. If you take the, for instance, this, let's go one more page here. The double integral of delta over a region where delta is a probability density function. This gives you the probability of finding something under a probability surface. And this is used in probability theory. Like, for instance, in the SAT scores, they do this with a one-dimensional function, the single integral of p of x dx from score 1 to score 2. The area gives you the area under the curve is the probability that the student will score between those two score marks. Similarly here, if you have a density function of 2 variables, you want to find what's the probability it'll be over this this result will have occurred within a plane region. You do a double integral like this. So that's one application, is to probability theory. Also, moments of inertia are in the end of the section. Those are a very important application of double integrals that we won't do either. They're not in the department problem set. But here they are down here. This is the page at the end, all the formulas. You can omit all this stuff on moments of inertia. It's not on the homework. Memorize all these up here. The centroid formulas, x bar, y bar, the area, the mass, you just integrate the density into 3 dimensions, and the moments, and the fact that the center of mass is moments divided by the mass. Putting in delta equals 1 turns these into the centroid formulas. By the way, also these moments in 3 dimensions, if you take the moment along the x-axis, we call it myz, it's the moment across the yz plane. Mxz is the moment across the xz plane, and myz is the moment across the xz plane. These are in complete analogy to the example we did with moments for planar regions. Well, try the homework problems. I hope that'll be enough to get you through them.